Hello everyone, my name is Olivia Chitarra and I'm a second year PhD student at ISMO in France, and I'm working with Olivier Pirali and Marie-Aline Martin. Today I would like to present you a project we developed at ISMO to study astrophysical radicals produced by a pulse-jet discharge experiment and detected with a Chirped-pulse millimeter wave spectrometer. But first, to understand physical phenomena and the chemistry happening in the interstellar medium, astrophysicists are implemented astrophysical models. To do so, they need to know which molecules are in the interstellar medium and which ones are not. To do that, they're using spectral catalog to be able to detect new species in the interstellar medium. For the detection, several spectral range can be used, but a very effective one is from the centimeter to the terahertz. It's very effective because it gives access to the rotational structure of molecule, a very unambiguous technique to detect, to assign new species in the interstellar medium. For example, ALMA is a very commonly used telescope based in Chile that covers the millimeter and submillimeter spectral range. To have access to those spectral catalogs, laboratory investigation is essential. So my PhD project is based on the laboratory investigation of species of interest to perform the rotational spectroscopy on those species to give spectral catalog to astrophysicists and maybe enable the interstellar detection. To do so, at ISMO, we have two spectrometers that cover the same spectral range as the one covered by ALMA. And we also have several setups that allow us to study stable molecules, but we also have several setups that allow us to produce and study reactive species like radicals. In this presentation, I will focus on the association we did between a supersonic expansion with an electric discharge and associated with a Chirped-pulse millimeter wave spectrometer. This technique was already published and presented at ISMS several years ago. And for our setup, we use an existing supersonic expansion chamber at ISMO that we associated with our spectrometer. And now I will present you how it works more precisely. The idea is based on three parts. First, we have the injection part. So we are injecting a precursor, an organic precursor seeded in a buffer gas that can be helium or argon with a typical dilution of approximately 0.5%. Then we are using a general valve that will create this pulse of molecule and will inject our organic precursor into the vacuum chamber. Thanks to this pulse, we can have access to this supersonic expansion and reduce the temperature to have access to a rotational temperature of about 10-20 Kelvin. There are several parameters that are very important, and one of them is the pressure that can be controlled thanks to the diffusion pump. But one very important aspect of this setup is the study of new species. To produce those new species, to synthesize them, we are using an electric discharge. I give you here a photograph of this electric discharge. And the idea is to put an high voltage on the outer electrode. We have two stainless steel electrodes, and we are putting high voltage on the outer electrodes. We can change the voltage and the resistance, and that allow us to test different conditions of currents. Finally, to probe what we are actually doing, to know what we are producing into this electric discharge, we are using a Chirped-pulse millimeter wave spectrometer. We are using a commercial Chirped-pulse spectrometer from BrightSpec that covers the 75-110 gigahertz spectral region. The interesting thing about this spectrometer is the broadband aspect. Instantly in the HDR mode, we have access to a segment of 30 megahertz, and it's very important for the study of new species, of unknown species and reactive species. We are using a quad powerful radiation of about 30 milliwatts, and the radiation is collimated and allows us to probe approximately 5 centimeters of this expansion. But more precisely, what we are doing. As I told you, we are injecting a pulse of molecule into the vacuum chamber. So we are triggering the radiation to disperse of molecules. We are sending the radiation at the moment we have the maximum of molecule. On this graph, you have the evolution of a precursor signal as a function of the delay between the moment the molecule are sent into the vacuum chamber and the moment we send the radiation. And as you can see, we have a maximum of molecular signal during approximately 400 microseconds. So during that time, that amount of time, we can send the radiation. The radiation is actually a cycle, so that lasts approximately 100 microseconds. So during the 400 microseconds, we have molecules, we have the maximum of molecule. We can send approximately up to 3 or 4 Chirped-pulse cycle. And in each cycle, we have first the pulse. So we are sending the radiation that will polarize all molecules present in the expansion. And then the polarization will relax by emitting a free induction decay. And this is what we're gonna detect. We are detecting the free induction decay. And on this free induction decay, we have all in the rotational information. So now I want to give you an example, the preliminary result we obtained with this precursor. So this is the acetonitrile precursor, so CH3CN. And first, we recorded the discharge of spectrum. It's a reference spectrum. And on this spectrum, we only have signal from the precursor. All lines correspond to the precursor, possible contaminant, but mostly from the precursor. It's an interesting spectrum because thanks to relative intensity of those transitions, we can estimate the rotational temperature of the expansion. And for this precursor, we estimate it to approximately 10 Kelvin. Then we are recording a discharge on. So this time we are switching on, we are putting this high voltage on electrode and producing new species. As you can see on the red trace, some lines appear. That means that we are producing new species. These very intense lines correspond, for example, to HCN produced by the electric discharge. So the next step is to remove all contribution from, from the precursor. We know where are the transition of the precursor thanks to the reference spectrum, so we can remove them from the spectrum. And by doing so, on that spectrum, all transition correspond to products, to species that have been produced by the electric discharge. So the next step is to use database like Splatalog to assign those transitions. That's what we did, and we were able to assign those transitions to several stable but also reactive species. The CH2CN and the HCCN species are reactive species, they are radicals. So we were able to assign, to produce and detect those radicals. We were also able to produce the HC3N molecule, and we were also able to produce it with another precursor, the CH2CHCN precursor, and that's what I want to show you. So with the acrylonitrile precursor, CH2CHCN, we were able to produce the HC3N molecule. And on this graph, you have 4 portions of one spectrum that allow us to follow a series of J for this HC3N molecule. All those spectral range have been aligned to the rotational transition within the vibrational ground state. And it's interesting because, as you can see, we were able to measure rotational transition within the vibrational ground state in red, but also in several vibrational excited states, V7, V6, V5, and V4. So it's very interesting. And using a formula published in Prosument in 2014, I give you the reference here, we use the formula to calculate the vibrational temperature. And you can see that it varies from 100 Kelvin to approximately 400 Kelvin. The error is quite large, and it's even larger for weak transition, because on the formula we are using the light intensity, and obviously for some line they are very weak. So the error bar is larger for those excited states. Finally, we wanted to focus on one radical. We used the acrylonitrile radical, so CH2CHCN, and we try to produce the alpha cyanovinyl radical. So it's the same structure, we just removed the hydrogen in the alpha position. This radical was already studied by Prosument in 2013, and in this spectral range, they were able to measure this transition around 78 gigahertz. So we focused on this specific spectral region around 78 gigahertz, and as you can see, we were actually able to measure the same transition. That means that the setup is working to produce the alpha cyanovinyl radical, but also to detect the radical. Finally, I want to give you a brief overview of some results we obtained. First, on this table, you have the results are already presented you with the spectrum with all the assignment. So on this spectrum, you saw that we were able to assign a lot of line. We were actually able to assign half of the spectrum. 51% of all line were assigned, but in terms of intensity, we were able to assign 99% of the spectrum. It means that all remaining peaks are very weak transition. It's quite different for the two other precursors, for the acrylonitrile and the methanol precursor that you have here, because for the two of them, we were also able to assign half of the spectrum approximately, but that corresponds only to 60 to 65% of the total intensity. That means that some quite intense transition remain on the spectrum and remain unassigned. So we don't know which species are responsible for those lines. So finally, what we did with this new setup, we were able to obtain a very efficient supersonic expansion. And thanks to this coupling between the electronic discharge and the Chirped-pulse spectrometer, we were able to produce and directly detect radicals in the expansion. All those species, except the alpha cyanovinyl radical, were already detected in the interstellar medium. So we produced astrophysically relevant species also. But what we want to do next is to continue the assignment of remaining lines. Some quite intense lines remain on the spectrum, and we want to assign them. There is several tests that we can perform, and one of them we already tried to perform it. It was by using a magnet, because thanks to a magnetic field, we can know if a transition arises from a closed or open shell molecule. Finally, we want also to test with new organic precursor or mixture of precursor to be able to produce new reactive species and maybe enable their interstellar detection. So finally, I want to thank all my collaborators, all the members of my team, and all the funding agencies. Thank you very much.